Hi, welcome back into Stat students. So today we are going to do this exercise called estimating p-values from simulations, right? Um, this is actually a very, very important idea, what a p-value is and the importance of simulation. So perhaps let me read through the questions and then we can discuss a little bit more about what p-values and simulation is. So, a class in New Zealand found a report suggesting that teenagers' heights in New Zealand are approximately normally distributed with a mean of 160 centimeters. Not very tall. 160 centimeters and a standard deviation of 15 centimeters. They thought they thought that the mean height at their school was probably larger. So they took a random sample, n equals to 24, right? Students, the mean height of students in that particular sample was had x bar equals to 166.5. So, I mean, if you look at this 166.5 from the sample and the mean was believed to be 160, standard deviation 15. Do you have any reason to believe that that 160 is incorrect? All right, from the sample that you took, your mean is 166, what is obviously greater than 160, right? And that proves maybe, right? That proves maybe what your school thought. Your school thought that you know that the mean height at your school was probably larger, and from the sample it looks like it. But is that really true? So to see how likely a sample like theirs was to occur by random chance alone, right? The class perform a simulation. So, ladies and gentlemen, this is what a simulation is. Simulation is like you run it as if by random chance alone that such a phenomena, such a event is taking place, and then you keep collecting data. You collect the sample after sample after sample, due to random chance, and see what the distribution looks like in the long run. They simulated 80 samples of size 24. So that size 24 of one sample, right, which the school did, they did that 80 times, 80 different times, right? So, with a mean of 160, standard deviation of 15, they recorded the mean of the heights in each sample. So each time they did a sample, they recorded the mean. And here are the sample means from their 80 sample. So here, the one sample that was previously done, 166.5. If you look at this data, where is 166.5? 166. So this is a unit of 2, right? Sorry, unit of 1. So 154, 155, 156, 157, 58, 166, and well, this is 167. So where is 66.5? 66.5 is right about here, right? Right about here. If you put it onto the simulation plot. And so how many of it is greater than 66.5? There, there are two. So one here, there are two. Two out of how many? Two out of 80. So by random chance, only two out of the 80 samples collected had mean greater than 166.5. That is your p-value, so to speak, right? So you want to test the hypothesis, right? The null hypothesis is that your claim, that New Zealand's teen's height is 160 centimeters, and then the alternate hypothesis is what you believed was to be true, right? You thought that it's going to be greater than 160. So that's your alternate hypothesis, where mean is the true mean height of teenagers at their school. Based on this simulated results, what is the approximate p-value of the test? So p-value is on the simulation, you pick the side. So here, this is greater than, right? So you put the sample here, and the sample was 166.5, which is about here. But because it's greater than, you're suspecting greater than, so we want to know how often does that happen? How often in the sample of 80, right, did you have sample greater than, your sample mean greater than 166.5? And out of 80, only two times. So if you take 2 divided by 80.025, and that's your p-value, right? That's your p-value. So hopefully that makes sense. I didn't remove my, okay. So next question. Let's do one more. A nutritionist suspected that her company's client had below average cholesterol. Yeah, that hope. They obtained a random sample of 8 clients of the same age and gender. These clients had a mean cholesterol level of X bar equals to 4.28, whatever that unit is, millimoles per liter. To see how likely a sample like this, all right, like this 4.28, was to happen by random chance alone, the nutritionist performed a simulation. They simulated 60 samples, right? 60 samples, and each sample is 8. There are 8 samples within that 60 samples. So they did this. They collected 8 clients, and then they find the mean, and they did that 60 times. All right, from a normal population with a mean of 4.6 millimole per liter and a standard deviation of 0.5. These are generally accepted values for people with the same age and gender of those in the sample. They recorded the mean of the cholesterol levels in each sample. Here are the sample mean. So here, what the claim is that it's 4.6, right? That's the population mean, right, of 4.6 cholesterol level. The standard deviation is 0.5. And your sample, you collected, the very first one that you did with the 8 clients is 4.28. Yeah, it is smaller than 4.6, but is it enough? Is it enough to say, the mean was wrong, right? It must be lower. It must be. Or could that 4.28 happen by chance alone? And how possible is that? That is the value of p value. Okay, so we can collect the 60 samples. Where is 4.28? So this is 4.1, 4.2, and 4.28 is about here. So how many samples that are less, right? That's your suspicion, right? You suspected that your company's client had below average, so below 4.6, but you got your sample mean to be 4.28. So let's see how likely, how often do you have something that is less than 4.28? So right here, this is where 4.28 is, probably less than. You have 0, 2, so 3. 3 out of how many? 60 samples. 3 out of 60 samples. 0.05, right? 0.05. Okay, so I hope this helps, right? 3 of the 60 simulated results were at or below X bar equals to 4.28. And this is how we calculate the p-value from simulation. So if you have any questions, do let me know. If not, thank you. Bye-bye.